that deal with the critical review of algorithms, application, and future perspectives of transfer learning for smart buildings. First of all, I want to thank all the other co-authors that span all over the world, in particular acknowledging that the work of Dr. Zhe Wang and Tianzhen Ong was supported by the Laboratory-Directed Research and Development Program of Lawrence Berkeley National Laboratory. And I want also to thank my supervisor, Professor Alfonso Capozzoli from Politecnico di Torino, to allow me to be here in Berkeley as a visiting PhD student. I decided to structure this webinar with a brief energy background, a theoretical background on transfer learning application, how we conducted the methods, and so the literature review, and then finishing with the review findings and future research opportunities. So, as you may know, the building sector consumes around 36% of the final energy, accounting for 40% of energy-related CO2 emission. And if we move from energy to electricity, this data increases even more, looking at the electricity consumed in the US, where buildings account for 70% of electricity consumption. So the role of smart buildings towards the energy transition is really increasing, because the three pillars that smart buildings has to follow in order to ensure the energy transition are the decarbonization that can be done integrating energy system and renewable energy sources, the digitalization that can be leveraged thanks to artificial intelligence in order to create advanced control strategies for buildings and providing useful information, and decentralization, basically just passing from smart buildings to smart communities and smart cities. In this review, we will especially deal with the digitalization part and how we can leverage machine learning and artificial intelligence in buildings. So in order to provide grid services, a building can leverage demand-side management. Basically, it means that they can change the demand-side loads to reduce the power demands when stress on the grid is high. And recently, the concept of grid interactive efficient buildings has been introduced that expanded traditional demand-side management, integrated distributed energy resources, sensors, data analytics, and advanced control. The aim is to provide benefits for the grid while reducing costs and optimizing user needs. In this context, machine learning has been seen as a viable resources to increase the efficiency of the building, as well as can be used in other building life cycle phases. For example, we have seen machine learning in the design, construction, maintenance, operation, and control phases of the built environment. And I've reported a very brief definition of machine learning that basically is training a software program with example, experiment, or experiences so that it can recognize patterns and make prediction, or even complete tasks. We have identified 4 main application areas for machine learning in buildings. In particular, occupancy and activity recognition, system control, load prediction, and building thermal dynamics. In order to exploit machine learning, one must be aware also of the domain expertise related to the building system. In particular, combining the domain expertise with data analytics through an intelligent layer, we can achieve what we call energy information system and automated system optimization. These are the 2 main application areas of machine learning in buildings. The energy information system is mainly related to the energy profiling, the demand prediction, FDD, advanced visualization, and occupancy detection, while the automated system optimization is related to the integration of renewable energy sources, demand response, adaptive envelope component control, and HVAC system control. The main target are the system diagnosis and maintenance, the optimal occupant management, and the predictive and adaptive control of all the energy system related to the building. However, despite the advantages provided by the machine learning, there are still some challenges that need to be addressed. In particular, the 2 most important challenges are related to the collecting and preparing a large amount of high-quality data to train machine learning algorithms. That nowadays is a time-consuming procedure that needs to be done for each new building. Furthermore, most buildings lack reliable sensing or metering system, or lack the IT infrastructure to collect and store this kind of data. Therefore, to address this gap, one key technique needed is to transfer machine learning model from one building to another building that has limited or poor data. And that is why we are trying to use transfer learning. During this review, we try to answer all these questions. So basically, we started with the motivation. Why should we use transfer learning for building research? How can we integrate it into the building research ecosystem? When to use it? How to transfer knowledge? What are the applications? And then, after finding the answer to this question, we try to understand what are the algorithms, tools, and how to assess performances. Lastly, we identified the future directions and challenges. Before diving deep into the review findings, I'm starting with some common knowledge background needed to fully understand transfer learning definition. Therefore, we will start from the definition of domain and task. Basically, a domain consists of two components, a feature space and a marginal probability distribution. While, on the other hand, a task consists of two components, a label space and an objective predicting function. The objective predicting function is not observed, but can be learned from the training data, and is used to approximate the conditional probability and predict the corresponding label of a new instance. Looking at the built environment, we can see that we have many examples. In particular, if we want to learn if our task is the electricity load prediction of a building, this is classically a regression problem, then the feature space is the space of all influencing variables, such as external temperature, occupancy, or historical load. While Y is a continuous space that includes all the possible values of the building load. The image on the right shows how, for each building, even despite there are some similarities, one should follow the same pipeline in order to achieve the load prediction. And transfer learning, in this case, is helpful to shorten this pipeline or even increase the accuracy of our models. The definition of transfer learning is the following one. Given a source domain and a task domain, and a target and a task domain, transfer learning aims to improve the learning process in the target domain using the knowledge in the source domain. Therefore, you should have at least the domain difference in the domain and the task. Transfer learning problems can be categorized based on different combination among the source and target domains, task, and solution adopted. We will see that the different classification that we are introducing will be useful to understand the review findings. In particular, we use three different classifications. The first one is a label classification that studies the task similarities and the label availability. Then we have a space classification that analyzes the similarity between the source and target space. And lastly, we have a solution classification that compares the approach used to transfer knowledge. Therefore, it aims to answer the question, how can we transfer knowledge? Looking at the image on the right, you can see that the transfer learning is may exploit a machine learning model for a specific building in order to improve or increase the performances on another building. Looking at the classification, we can see that the label classification is further divided in three subsettings. The inductive transfer learning setting, the target task is different from the source task, no matter whether the source and target building are the same or not, and no assumption on data availability, on label availability is done. In the transactive transfer learning setting, the source and target task are the same, while the source and target domain are different, and we have no label in the target domain. Lastly, in the unsupervised transfer learning setting, the target task is different but related to the source task, and there are no labels available. On the other hand, the space classification categorizes transfer learning in two subsettings. In the homogeneous case, the feature space and the task are the same. Otherwise, if some differences arise between the feature space and the task, the transfer learning is defined as heterogeneous. You can see from the table below that the two classifications can coexist and lead to 4 different cases. Just looking at the first one, you can see that homogeneous inductive learning means that the domain, in this case, is the feature space is the same. Therefore, you can see xs is equal to xt, while the task is different. Giving an example, it means that transfer learning is used to enhance building monthly electrical load prediction, leveraging information from similar buildings in different districts that exhibit a different conditional probability. Therefore, in this case, the difference in the task is expressed by the different conditional probability. Lastly, we have the solution classification that categorized how transfer learning can be applied with 4 different ways. The instance-based exploit data from similar environment to enrich the target data. The feature representation analyzes the similarity between the feature in the different environment and also allows you to use other domains as a starting point. The model parameter uses the parameter of a machine learning model as a starting point to increase the performances of the target model. And this can be done in 2 ways that we will later be analyzed. Lastly, the relational knowledge studies the relations in multi-relational dataset. And this one is the least applied in the build environment because of the nature of the dataset that we currently study that are mainly focused on time series. Looking at the model parameter-based transfer learning, we can see that it may be divided in 2 subsegments. The first way is to use the pre-trained model for feature extraction. This has the main advantage to exploit data from different domains, such as computer vision, that are domains in which machine learning has been heavily exploited. The second way is to use the pre-trained model for weight initialization. In this case, you just use pre-trained model as a starting point, and then you proceed to fine-tune in order to tailor the specific model to the target analyzed. In order to perform the literature review, we combined sub-keyword synonym searching with the domain knowledge. This has been done for multiple reasons. The first topic search was performed simply combining the words transfer learning and building, because it was needed to obtain a broad overview of the topic analyzed. However, we saw that the word building may be related to building a machine learning model. Therefore, we exploited our domain knowledge to identify 4 main application areas, performing sub-keyword synonym searching in order to obtain more precise results, avoiding errors. In particular, we have identified 4 main applications: building load prediction, occupancy detection, building dynamics, and building system control. The literature review was done in June 21, and this methodology allows us to use also synonyms during the research, because building load prediction can often be referred as energy forecasting building, despite being the same research field. So with this methodology, we ensured that we were covering all the possible papers analyzed. After the review was conducted, we found 77 papers. And as you can see from the image in the top right, we found the paper from 31 unique countries, with the most contributors from China, USA, Australia, Canada, and Japan. On the other hand, looking at the image on the bottom right, we can see that the distribution over the years and journals has increased in the recent years, especially in the last 5 years. And that there is a lot of interest in the energy and building fields, followed by IT fields. Looking at the keyword word cloud, we can see that the neural networks are the most widely used techniques, as well as deep learning and reinforcement learning. Lastly, we decided to deep dive into the main application area of transfer learning. And we found that the load prediction represents 30% of the reviewed paper, while in the last year, there is an emerging interest for transfer learning in building dynamics and system control. Then we also show a parallel categorical plot on the bottom that relate the 3 different classifications introduced before. Therefore, the solution classification, the label classification, and the space classification. This graph was useful to understand the main trends over the different classification. And we saw immediately that the parameter-based solutions are used in around 75% of the cases, and that supervised transfer learning is used only for occupancy detection and activity recognition. These are mainly intrinsic characteristics related to the problem analyzed, while the space classification didn't have any major major insights, because it is really needed. It is really depending on the similarity between the source and the target domain. Now I will deep dive into the specific application, starting from the load prediction. As you can see, 30% of the paper use transfer learning with the aim to facilitate more accurate, data efficient, and robust load prediction. In particular, transfer learning for load prediction can be performed at high different scales, starting from single appliances up to the entire city. But the most common application that we found are transfer learning for non-intrusive load monitoring at sub-hourly resolution and whole building load prediction at hourly resolution. The approaches use mainly parameter-based transfer learning with LSTM for whole building and time series in particular, while non-intrusive load monitoring leverage computer vision domain and CNN to analyze images. The results show that transfer learning could help overcoming data unavailability, generalizing over different buildings. Moving from the most analyzed to the least analyzed topic, we found that only 7 papers use transfer learning in energy system control, with the aim to facilitate the deployment of advanced control strategy. In particular, all these papers exploited a policy transfer approach in combination with reinforcement learning to optimize control at different scales, from microgrid to batteries, HVAC systems, and single appliances. In this case, the results show that reinforcement learning and transfer learning can represent a suitable alternatives where there are not a lot of data, and the main advantage is the speeding up process of reinforcement learning. However, further studies are needed to demonstrate the ability of transfer learning to generalize across the building with different energy systems. In fact, all the application analyzed dealt with the homogeneous transfer learning. Therefore, there is still new studies are needed to assess the capability of transfer learning in this application, therefore the system control, when there are considered heterogeneous systems. Going ahead, the building dynamics paper, we're focusing on the use of transfer learning to develop building dynamics model. This kind of model are mainly used to predict room internal temperature evolution, while a few applications applied also the same model to predict humidity and storage evolution temperature. The main approaches in this case are still parameter-based transfer learning, but with application of LSTM and MLP. The results show that this kind of application can enable a faster deployment of advanced control strategies, removing the need for white box modeling and easing the deployment of advanced techniques based on data-driven. However, there are still further studies needed to quantify the impact of different features. In particular, the difference in weather, forcing variables, and occupancy can really affect this kind of models, and further studies are needed. The last application area among our 4 application areas is the occupancy detection and activity recognition. That represent the second most interesting, most studied application. In particular, the occupancy detection leverages CNN and LSTM, as well as feature-based transfer learning to exploit both time series data and images. While, on the other hand, activity recognition mainly use feature-based transfer learning. That is the second most used transfer learning technique in an unsupervised settings, because it can rely on camera images that are not labeled. The results show that in this case, the main advantages of using transfer learning is not just to increase the performance or to overcome data unavailability, but to overcome the absence of labeling data. And also, it can be used to leverage computer vision domain. Other applications represent around 25% of the paper analyzed and includes FTD, metadata models for buildings, PV damage detection, building identification, and air pollution. These applications mainly leverage parameter-based transfer learning, using image recognition dataset and pre-trained models to speed up the performances. Now we will shift from the application to the techniques, therefore to the different ways of transfer knowledge. As you can see from the graph on the left, there is really a disproportion between the technique used, and the parameter-based represent around 75% of the technique analyzed. Especially during the last year, they represent the vast majority of the applications. And among parameter-based transfer learning, we have seen that there are two ways of transferring models. In particular, the weight initialization, in which you start from a pre-trained model to fine-tune the model on the target, is the most common one, while the feature extraction is mainly related to classification tasks. However, few studies compare both methods of transferring knowledge for the same application. Lastly, we try to infer the type of application with the type of parameter-based transfer learning. And we discovered that the building dynamics and system control uses mostly weight initialization, while on the other hand, load prediction and other applications can use both techniques in the same amount based on the specific problem. Lastly, looking at metrics, it can be seen that, of course, the metrics used are depending on the problems analyzed, and we can mainly divide the problems in classification problems and regression problems. The classification problems use the accuracy as the most common metrics, while the regression problems employed RMSE and MI. However, it should be seen that few studies deep dive into the metrics used for transfer learnings. In fact, indeed, despite using most common metrics to quantify the increase of performances, they didn't quantify the most common metrics in transfer learning, that are the jumpstart, the time to threshold, and the asymptotic performance. In particular, the jumpstart is used as a metric to quantify the increase in initial performance achievable using transfer learning, while the time to threshold is used to quantify the amount of time it takes to achieve certain performance. And these kind of metrics are especially useful when looking at industrial application, where certain threshold needs to be reached before deploying the model. Lastly, the most common way of comparing a transfer learning model with a machine learning model is to look at the asymptotic performance, or to look at the performances on the test dataset. And the comparison between these two techniques used to assess the performance improvement of the transfer learning over the machine learning. Now, looking at research trend, we have seen that load prediction is the topic with the highest number of publications, but this is mainly due to the meter level data availability that is more common. Parameter-based was used in the 75% of the papers I already seen. That is an astonishing number, and we have assessed the recent use of LSTM for regression problem and CNN for classification task. Building dynamics, on the other hand, represent the topic with the highest interest in the recent years due to the opportunity to be coupled with advanced data-driven controller, or with the advanced techniques such as MPC or reinforcement learning. And despite reinforcement learning applications still exist, they are in their infancy, requiring further study. So now we will try to also answer the question that we posed in the beginning of the webinar. So why should we use transfer learning for energy and buildings? The main reason is that transfer learning allows to scale up machine learning, increase performances in absence of data, in case of absence of data, and to also speed up machine learning, because we've seen that the jumpstart can allow to quantify the speed up of machine learning process. The transfer learning integrates in many ways in the building ecosystem, starting from the leveraging advanced metering infrastructure to improve information system. And the main application for the use of transfer learning are related to the scarcity of data. So what are the challenges? Right now, further studies are necessary to propose robust methods on how to select the right source building in order to avoid a negative transfer. Furthermore, it is still unclear the amount of data necessary in the source building to perform a proper transfer knowledge, because it depends heavily on the application analyzed. Furthermore, there are also specific application challenges that are related to the reinforcement learning. And despite the potential of transfer learning for energy system control, as I told you, the the reinforcement learning was mainly applied in homogeneous case. Therefore, many studies are needed to quantify the effectiveness of transfer learning for heterogeneous case and to ensure a safe control policy that does not preclude user comfort or increase costs associated with control. So in conclusion, we can say that transfer learning can be used for energy in buildings because higher data availability in buildings is leading to a data-centric energy management. And transfer learning can easily support the penetration of machine learning for energy management in buildings by contributing to reduce implementation costs and time. The natural use of transfer learning can be found in existing buildings, recently equipped with monitoring infrastructure or new building with limited historical data. And the review allowed us to identify the main research gap and future direction. In particular, there is still no clear way to identify the right source building, especially for applications such as building dynamic forecasting and system control. And we need a way to ensure the safety of the transfer control policy in the system control application. Furthermore, I want to highlight that workflow standardization and open source codes are fundamental to increase the reproducibility of the work in the machine learning field, and that common guidelines and high quality datasets to benchmark the different transfer learning approaches are necessary. So now I just want to show you some of the future research opportunities that we are trying to pursue with the different lab and collaborating with. The first one is the transfer learning for building thermal dynamics, a statistical investigation on influencing factor. And the second one is the creation of a framework that introduces data-driven models and controllers for smart communities. The first research topic is mainly related to the question that we previously introduced. Therefore, how to select the right source building? What is the minimum amount of data necessary to obtain good transfer learning performances? But most importantly, what are the most influencing factors on the effectiveness of transfer learning? We try to study this question for the application of building thermal dynamics. In fact, we want to exploit transfer learning to scale thermal dynamic model in smart buildings. We are doing so by leveraging a synthetic building operational dataset with over 1,000 simulations that span over different climates, efficiency level, occupancy schedules, and multiple years of data. We have created a methodology that divides the influence of machine learning related variables and building related variables. Therefore, we are studying data availability, AI technique, climate, efficiency level, and occupancy profile. And all this combination leads to over 250 machine learning models that will be deeply investigated to assess the importance of each specific feature. Lastly, during the last year, we introduced a data-driven framework to support the district energy management using surrogate models to predict building dynamic evolution and deep reinforcement learning. Therefore, we introduce a framework that exploits both data-driven models and data-driven controllers. Now, in collaboration with several universities, we are trying to introduce a framework based on data-driven controllers and models that is able to exploit occupant-centric control, thermostatically controlled loads, CityLearn Core, that is a simulation environment that allows the control of thermal and electrical storage in multiple buildings for demand response, and GridLearn for voltage control and smart inverters. We are doing so because we hope that combining all these applications, we can create a framework that exploits both data-driven models and controllers, such that we can also implement transfer learning, starting from the occupant-centric control up to building thermal dynamics and reinforcement learning. Therefore, this benchmark should be able to allow anyone to test the transfer learning performances of almost each kind of application. Thank you. And for more information, visit www.baida.polito.it.
Okay, thank you, Mr. Pinto. For our audience, there are two questions about your presentation today. So the first is that Mr. Zhao asked that what kind of software were you are using for those drawings or tables in your presentation? It's very interesting.
Drawings or tables.
What kind
okay.
of program or software for those tables or drawings?
Yeah, okay. So for tables, I think that I use Overleaf, that is the online version of LaTeX, while for drawings, I mainly use for the graphs Python with in particular, I think I use Plotly for this kind of graph that I will show you right now. This kind of graph, the parallel categorical graph. While for the other, just mainly Python with the Matplotlib and Seaborn libraries, and PowerPoint for this kind of figures.
Okay, thank you. And then here's another question that mentioned that when you using parameter transfer learning, freezing some or not of the trained models for Y, how to consider and explain it?
Okay, so I just want to show you also the question to the other. So basically, there are two main subfields of model-based transfer learning that are the feature extraction and weight initialization. So from the review, we have seen that feature extraction was mainly used for classification problem. This is because it is easy to leverage big data sets such as ImageNet or already built deep neural networks such as AlexNet. You can just freeze the parameter and fine-tune the first and last parameter in order to let the neural network understand the relation with your specific dataset. And this is mainly done for classification purposes. On the other hand, we found that weight initialization is more common when dealing with time series. So it's really easy to use the pre-trained model as a starting point and then fine-tune on your small target dataset.
Okay, and here's another one. Can you provide a high-level explanation on why transfer learning works and what kind of condition it may fail and why?
Okay.
Can you talk more about the negative transfer in the general and how to avoid it?
Okay, really tough question, but really interesting. So the main concept, the main idea behind the application of transfer learning is that in many times buildings are more similar than different. Therefore, there should be a way to infer the similarity to a neural network, for example. I will just, for a simplicity purpose, I will just focus on neural networks because we have seen that is the most used application, most used technique, sorry. Therefore, we just want to infer the similarity between buildings through the model parameters, so through the weights and biases of the neural network. And however, this can be helpful, or this can be really a bad idea. In particular, the so-called negative transfer can happen, but I will say that it really depends on the data availability that you have. So if you have really poor data on the target building, maybe it can be more helpful to start from to use a source building with like 1 year of data and then apply transfer learning, because the building thermal dynamics, for example, even if slightly different, follows the same physical rule of the other building. While for a neural network, starting from scratch, a single week of data may be too low, too little to fully understand the physical law that control the behavior of the building thermal dynamics. So to sum up your question, you should avoid to use transfer learning if you think that the two data sets that you are dealing with are really different, and especially if you think that the task is really different. For example, I will not use a data set that starts from the building load prediction to quantify the occupancy detection without a specific study. I will rather use a model that was already trained and tested in a real life environment for a building load prediction to support me in the creation of transfer learning model for the building load prediction. So the easiest way is to stick with the same application to avoid negative transfer. I hope that this answers your question.
Okay, Mr. Patrick asked that, are there pre-trained models for regression text as there are for image classification?
Yeah. So for regression task, I'm not aware of any specific model, but I will say that also the model that are pre-trained for image classification can be really used for regression. For example, I want just to show you the CNN cases here. I've spoken about non-intrusive load monitoring. Basically, the non-intrusive load monitoring is just a time series that is has very few occurrency with the high spikes. In order to overcome the unavailability of regression pre-trained neural network, they converted this kind of time series in an image and used already pre-trained neural networks based on image classification. So the turnaround, the trick is just to convert your time series into image, and then if you think it's necessary, you can also use the pre-trained models for image classification.
Okay, Mr. Patrick asked another curious questions. So based on the recent share predictor competition results, tree-based algorithm performed better than neutral networks. Did you check potentials of transfer learning use tree-based models?
Yeah. However, first of all, I also read the news and it's very interesting. And but I will say that the building energy, the application of machine learning in building energy field, despite being very interesting, is less broad with respect to many other machine learning application in general, such as computer vision. Therefore, despite we looked for this kind of application, we didn't find any relevant literature during the review. But we have seen a similar application in the instance-based and feature-based. However, it is hard to compare the two papers based on different application in terms of performances. That's why I think that also a relevant research question that should be answered is to compare different kind of transfer learning techniques on the same data set.
Okay, and here's another question from our other Bilibili, and it mentioned that if applying the transfer learning to control, is it still effective for different systems?
Really interesting question. Really interesting question. I have to say, we are currently also studying it with a colleague of mine that just started this kind of research. I will say is the most interesting topic at the moment, but also the most difficult one, because the transfer learning application and system control is really dependent of the data availability and on the fact that you should ensure a safe control policy. So as long as you produce a safe control policy, it should be fine to transfer knowledge. But right now, the only applications are limited to the same energy systems. Therefore, I think that the main barrier right now is to start controlling very different energy system, and hopefully see that we do not have any safe control policy problem. But it's still it's really still in its infancy, and we found only 7 relevant papers. But yeah, I hope that in the future I will be able to read many more interesting papers on this topic.
Okay, I think there is an audience want to ask you in person.
Yes.
Mr. Yes.
Yes. Hello, I'm Mustafa. I'm a PhD student in Concordia. Thank you so much for this presentation. I wanted to ask mainly about the case of synthetic data sets, not like what I understand, you're mainly talking about available data sets that we need to pre-process and then try build a machine learning model on one and try to transfer what we have learned from this model on another one. But I want to ask mainly about synthetic data sets. So data sets that we actually created based on an Energy Plus model. What is the success rate of transferring the prediction of one model to another unknown building that we haven't saw, or like, for example, from a residential building stock to an office building stock, for example?
Okay. Okay, really interesting question that is also among my future works. So I can really feel an interest. But right now, I think that the topic is so broad. If you want to characterize each influencing factor, that first of all, you need synthetic dataset, because there is no amount of data to simply assess the influence of a single specific factor, such as freezing all the other influencing factor and changing only the climates. So among these influencing factor, that is also the use destination of the building. And right now we are just focusing on the building construction materials and the occupancy schedule, but just remembering a few simulations that we have recently done during this week, I will say that there is a high success rate in transferring even from a specific zone to another zone with very different occupancy rate and exposition. So the influence of solar radiation is really different. But we still have to understand if this kind of model can be really transferred from a commercial building to residential building. So I would say is an interesting question, but probably among the future work that needs to be done.
That's great, because we're working on that actually here in Concordia. So we're collaborating also with Dr. Auf's lab and so on, and the Next Generation Cities Institute, where that's what I study in. But mainly we're working on similar things, and it would be great, like if a collaboration could be developed from that. But very interesting presentation, and I read the paper actually, and it's very interesting. Thank you for that.
Thank you. Thank you very much. I mean, for sure, we can have a follow-up later.
Yeah, thank you. And here's another question that you mentioned that during your study, is the data privacy a problem?
Yeah, you're right. And that's the main reason why we try to overcome this problem using a synthetic building operational dataset, because in this case, you don't have any data privacy problem. In my vision, I mean, this kind of approaches could even become a service. So if a company wants, he can sell its specific data in order to facilitate the deployment of other models. But of course, the data privacy is really delicate problem and should be addressed, especially looking at starting from the bureaucracy. That's why I think that one of the easiest way is to start also from commercial buildings, because residential building may be even more complicated to deal with.
Okay, thank you, Mr. Pinto. Is there any other audience have the question? Okay, it seems so we have a very hidden discussion today about the transfer learning and about the other things like data privacy and also the other like systems applications. And then so please remember to contact Mr. Pinto if you are interested in his study, and also keep an eye on our Energy Visions forum for the next seminar. And then so let's call it a day. And thank you very much for your time. And thank you for our speaker today. And then, okay.
Thank you.
Thank you, everyone.
Bye-bye.
Bye-bye.